over my words and then getting caught in a fire drill. Were there any chapter 15 questions that we wanted to do, Hannah? 126, you say? 122, sure. Oops, I grabbed a little too much there on the edges, but whatever. All right, so the first order of business is I'm going to get rid of the fraction. So I'm going to just go multiply both sides by 2. Cool there. And then I'm going to multiply both sides by 2 to the x. And that's going to give me a 2 to the x squared plus 1 equals 6 times 2 to the x. And I wanted to do that because it's going to get rid of that negative exponent, because I know that's another fraction in there. I'm going to move everything onto one side. And then we'll think about this like a quadratic. So if we do that, it's really like y squared minus 6y plus 1. To solve that quadratic, I could try factoring, but obviously there's not two things that multiply to give us 1 and add to give us negative 6. So we have to use the quadratic formula. I have an extra symbol there. Okay. So 36 minus 4 is 32. So that's going to be 4 root. The square root of 32 is just 4 root 2. And that'll all reduce down to that. But we're not solving for y. We want to solve for x. So if I put that back, I'd have this. And then to get rid of the exponent base of 2, I'm going to use log base 2. And at that point, it's calculator time. So to get the log base 2, I'm going to press math and use the log base command. That'll allow me to just type it in. You could use the change of base formula too if you wanted, but no worries. So there's my first answer. And if I try to do the second one, there's my second answer. And that's all she wrote. Does that feel okay?
Yeah.
Okay. Who else? Do we have any others? Questions? Bless you. You're welcome. Okay. Then let's pick up where we had left off. This is, I think, section 5. So we had, last time we had been talking about our compound interest formula, right? So we talked about specifically this K being the number of compounds per year. The question is, what happens if we are, say, in compounding continuously? What value of K would that imply? What does continuously mean? Yeah, that's right. Infinite. Now, can I plug infinity into this formula and evaluate anything? No, right? So we got to find a better way of doing that. So let's kind of just see what's going to happen. So keep in mind that eventually we're going to want to put k in as an infinity, or at least, approaching infinity. But let's just kind of start with what we have here. And we're going to start by, I'm going to let x equal 100k over r. So if I do that, r over 100k becomes just 1 over x, right? Everybody's cool there? And then in the exponent, I'm going to multiply that by just 100r over 100r. And that's certainly okay to do, right? Since I'm just multiplying by 1, really. And you might think to me, Mr. Kulik, why are you just multiplying by 1 in the numerator there? Or in the exponent there? Well, it's because if I do that, I can rearrange and make 100k over n times, not over n, over r, to have nk over 100. Everybody see that? I just rearrange some stuff. And looky here, why'd I rearrange it? It's so I could get x there. And then I'm just going to write it like this. It's multiplication. So now what I do is I note, hey, that as k goes to infinity, x equals 100k over r, that also would have to go to infinity as well, right? Everybody's okay with that? So if I take a look at this piece here, and I look at the limit as x approaches infinity of this, does anybody recognize that? We talked about it earlier this chapter. This is something. Carmen? It's not the logistic function, but it was kind of related to it in that neck of the woods. This is E. That was our definition for E. Yeah. So what can I do then? All that stuff I highlighted in yellow, I can just replace with E. And there's our familiar continuously compounding interest formula that you probably go, oh yeah, we did that last year. That makes sense. There's where it comes from. That's fun, right? Did you do that derivation last year? Probably not. It's a good one, though. All right. Quick numeric example here. So Jack invests $800 into a savings account with 5% annual interest compounded continuously. How long will it take for Jack to have $500 in interest? So I know that the future value should be the present value plus the interest. So we're going to be solving this for 1300 equals 800 e to the negative 5n over 100. Why did I write negative? Dum-dum. There's no negative there. Excuse me. It's okay? It's all right. All right, how would I go about solving this? First step would be to? Good. I'm going to reduce that fraction while I do that. And let's be real, Mr. Kulik. We'll just make that n over 20. I'll reduce that fraction too. Okay, what's up next?
Natural log.
Great. Why did you choose the natural log? Because it's log base e. Good. And you need the log base to match the exponent base. I shouldn't say need, but it just makes life a lot easier if the bases match. And if you have the choice, why not choose to make your life easier? My life's hard enough. Life one-handed stinks. And then we just multiply our both sides by 20, and that's our last step. And from there, it's just calculator time. So let's punch that through real quick. And I get 9.7-ish. Everybody okay there? Okay. So we have all these different possible number of compounds per year, right? So we have annually and semi-annually and quarterly and monthly and hourly, whatever. How would we go about comparing one interest rate with some number of compounds per year versus a different interest rate with a different number of compounds per year to find out which one of these is actually the better deal? So that's what we're going to be exploring here in this example. So we have a 6.5 annual interest rate compounded monthly. And we want the equivalent interest rate that would be compounded annually, right? Oops, that's not R, that's 6.5. But this one's R because we don't know what that is. Everybody agree there on what I filled in? So if I look here, for those to essentially be the same rate, that part, which I could consider the b of my exponential, just needs to be equal, right? If I set those two things equal to each other, then everything else is the same, so I'd have the same function, right? So I have this. So to solve for r, I'm just going to subtract 1 from both sides and multiply by 100, because there's no need to use a radical or anything, because it's just to the first power there. So I get about 6.70. And this idea actually just turns into a definition then. So this idea of like, what is the interest rate in a given situation, if I convert that to just like the equivalent annual interest rate, is what we call APY, or the annual percentage yield. So it's just a way to compare two different scenarios of like, oh, I have this interest rate with this number of compounds, and I have this interest rate with that number of compounds. Which one is really better? I'll just convert both of those situations to an APY and pick the one that's bigger, right? That's the idea. So this is our formula that we have for the APY, which is exactly what we ended up doing, right? So let's do a quick numeric example. So we have two situations. We have which saving account is better. We have 7.8% compounded quarterly versus 6.5% compounded weekly. So again, all we're going to do is convert these into APYs. Just put a subscript on those. And just calculator time now, just like filling into a formula and then doing a little plugging and chugging. So one is essentially an 803. The other one is going to be some number that we'll find out shortly, as I'm just kind of dancing in place while I press the buttons on my calculator. 794. And if I'm picking which one is the better investment, I'll pick the bigger one, because it's going to mean more money for me. Everybody cool with that? Okay. Last situation that we're going to talk about is the idea of what's called an annuity. So up to this point, we've been talking about situations where you make like one lump sum investment and then do nothing over time. Most of our investments don't look like that. What do investments look like? You should probably save a little bit of money every month, right? So that situation is called an annuity. And when you save the same amount of money every month, which is pretty common, like that's how people's retirement savings kind of work. So they pre-select, we're going to put this much money away every month or whatever. It's called an ordinary annuity, and that's what we're going to be talking about as our final topic. So we have that annuity is an account in which a sequence of payments are made An ordinary annuity is an annuity that always makes the same deposit at the end of each period that the interest is calculated on the account. So that's basically what we just talked about. The future value of an annuity consisting of n ordinary payments of PMT dollars at an interest rate per compounding period of I is the formula given below. Note that I is just going to equal our R over 100K, and N is going to equal, or cap N should be equal to K times little n, where all of these things are the same as the compound interest formula, right? Little r is the interest rate as a percentage, K is the number of compounds per year, little n is the number of years. So let's do a numeric example, kind of getting used to this. All right, here we go. At the end of each quarter, Sarah makes a $500 payment into an annuity account. What is the $500? That's the payment. That's the PMT. If her investments earn 7.88% annual interest compounded quarterly, well, that tells me the 7.88 is my R, and the quarterly is my K. What will the value of Sarah's annuity, well, that's the future value, be in 20 years? So little n is 20. Everybody cool with how I discern that? Okay. Plug in time now. Remember that little I is interest rate divided by 100 times the number of compounds. And then cap N is the number of compounds times the number of years. So that's what we're going to be typing into my calculator. Now, I would encourage you to do this kind of all in one shot. But we have to be a little bit careful about this because this is getting like pretty confusing fractions inside of fractions inside of fractions. So what I'm going to do is I'm going to take advantage of the STO command. So I'm going to do the 7.88 divided by 100 times 4. And I'm going to store that by pressing the STO button into the letter I. So now, when I type this in, it's going to be a little less confusing. I am still going to use the fraction command here, but I'm going to just have 1 plus, and then I can just do I to the 4 times 20. Don't forget your minus 1. It's easy to do that. Over I. And then I can just kind of avoid having the fractions inside of fractions by kind of doing it in 2 steps there. So what do I get? I get $95,483.39. Not too bad. What other kind of situation does an annuity kind of sound like, though? What about paying off a loan, right? That's kind of the reverse idea, is that you're given some present value up front. You're going to make some regular payments on it until you get down to like 0, right? So let's kind of look at what that would look like. So the net total, or the amount of money that we borrow for a loan, we're going to call the present value or the principal value. It's just the PV. The present value of a loan consisting of n equal payments of PMT dollars at an interest rate per compounding period of I is slightly different version of the previous formula, right? So there's a negative sign that it was applied through, and we have a negative exponent, but like other than that, it looks basically the same. Let's do an example real quick of working with this. Actually, I have two examples working with this, and then we'll call our goods for today. So Maria buys a new car for $18,500. What are the monthly payments for a 4-year loan if she makes a $2,000 down payment and the annual interest rate is 2.9%? When we say down payment, does everybody understand what a down payment is? So the price of the car is $18,500. What does the down payment mean? I'm paying for $2,000 of that $18,500 right away. How am I going to get the rest of the money? I'm borrowing it, right? And I'll pay it back later. So what was my present value? It's the cost minus the down payment, because that's what I'm actually having to borrow. Everybody's okay there? Okay. Little n is 4. Interest rate is 2.9. K is 1. And let's rock and roll here. So I have $16,500. That's what I'm buying or borrowing. And then I have the PMT, which is what we're going to be finding. Oh, shoot. Yeah. So the K isn't 1 here, dum-dums. K is 12. That's my fault. Woo! Got it. It's like those are going to be some massive monthly payments if we're only making 4 total payments on this. Okay, so there's that. I'm going to do this kind of the same way. And I'm going to do it basically all in my calculator, right? So I'm going to start by calculating that value for I. And storing that. And again, I like to use the letter I because it matches the letter in the formula. And then I'm going to do fraction 1 minus 1 plus I to the 4 times 12.
Like that exponent should be like negative.
Oh, yes, thank you. Yep. Good thing you stopped me before we pressed enter. Thanks, dude. I would have been sitting there going, what the heck? What the heck? It's my daughter's favorite expression now. All right, so I have that. And then I'm going to do 16,500 divided by that answer. So I should be paying $364.49-ish. per month. So quick question, how much did I end up paying for that? How much did I end up paying for the car? Well, like exactly, how much would I, like exactly numerically, how would I figure that out? I paid this much every month for 4 years, plus the $2,000 I put down. Actually ended up paying $19,495.41 for the car. So that cost me about $1,000 in interest to have to borrow that money. Everybody cool? Oh, that's what we just did. So my last example was just that. How much interest did we pay from the loan? So I just took my total cost and I minused the price of the car. And there's my amount of interest paid, right? I'm not going to write any of this down because it just did it all in the calculator. You know what I'm saying, guys? Now, if you're taking a test or something, you probably want to like at least write down what you did, so that if you fat fingered a number or something, I can give you a lot of credit for knowing what to do and just like not executing well. You know what I mean? But that's it for chapter 15. That was the last idea. So you guys can now be effective car loan negotiators. Be like, hold on a second. What are the terms here? I can calculate my monthly payment. I don't need you. I'm sure they just have a program at their desk where they do it. It's probably a little bit more sophisticated than this because like when you make your payment kind of matters also. Like it's like a whole thing. All right. That sounds good here. What do we still need to do?